Okay, so last time we had covered a lot of what's in chapter 9, which is dealing with this prediction in the case of approximation. And in order to do this, we had defined this prediction objective, which is different from before, where we weight the error with the true value function, but it's weighted according to the on policy distribution. In this case, we're approximating the value of this policy pi. And this is in some ways like an arbitrary choice, but it is a natural prediction objective. I mean, like the squared error that, but there's no like really excellent reason to use this other than it's a convenient choice and it makes taking the derivatives that we need to take pretty easy. But the main difference from the previous section is that we now have this on policy distribution where this is, the frequency of states that are visited under this policy. And this is necessary because in general, our approximation um, will be like states will affect each other in some way. So if we improve the value of one state, it may be detrimental to the value of other states. So this controls sort of the importance that we place on each state. The states that are, of course, visited the most frequently will have more importance placed on them. And there was this nice picture of that for this random walk example where if you look, this is in the case of, we talked about this last week, but state aggregation where we just bucket the states into some set number of groups. So the approximation has to be the same for every state in the group. You can see for the states on the edge, the approximation is closer to the true value of the states that are closer to the center. And that is because the states closer to the center are visited more frequently. If you look at the picture, or where do we have it? Well, in the book, there's this picture of the on policy distribution for this random walk where you could see, the closer you get to the center, the more frequently the states are visited. So the approximate value for this particular technique will always, place more weight on the states closer to the center. Okay, so that's sort of the general picture. This technique being like the simplest linear technique that you could use. And then we had gone over a number of other, well, we had talked about the the linear method in general, where our approximation is just an inner product between the weight vector and some feature vector representation. Now, in order to use this technique, you have to actually construct, oh, sorry, this should actually be x of s here. Not, yeah. So in this case, like x of s refers to, some function that transforms a state s into a feature vector. And in the case of this like state aggregation, the feature vector that is being constructed is actually like a one-hot vector that just maps a state to a particular index. So like practically you don't have to form that vector, but that is like what the feature vector is. It's the simplest feature vector that you could imagine making. And then, this function could be anything. Chapter 9 covers a few different possible techniques for constructing the feature vector, but once you have it, the update rule becomes a lot simpler because our approximation is just defined as this inner product between the weight vector and the feature vector. And the gradient also has a particularly simple form where it's just the weight vector. So this is what the update is in the case of Monte Carlo returns, where again, we're replacing the true value with this, some unbiased sample of the true value. And in the Monte Carlo case, this is just G sub t, where G is the actual observed discounted return for an episode. So then we had talked about how with TD learning, we replace this U with this TD approximation, right? Where this is a one-step look ahead, where we're actually using our existing value approximation. And this doesn't require us to complete an episode because all we have to do is take one step and observe the reward from taking one step. But we are having to actually use the current weight vector to form this UT estimate. And that itself means that the technique we were using with the gradient, taking the gradient, is no longer correct because this formula that we had assumed that UT was independent of the weight vector. That we didn't also have to take the gradient of UT. But by writing this, we're clearly using an approximation where the weight vector is present in the approximation. So technically, we should incorporate that into the gradient, but for this technique, we're not going to. And that means that these temporal difference methods were called semi-gradient techniques because the thing we're computing is not actually the true gradient. So what we had kind of lost over before was this analysis of, in the linear case, of how this still converges to something. But what it converges to is actually the TD fixed point instead of the function that minimizes the value error, which is what happens here. So for the Monte Carlo method, because it's a true gradient method, we actually if we do take this for enough episodes, enough steps, this will converge to what should minimize the value error. And in the TD case, you can actually rearrange this formula for the TD update, and you can write it in such a way that you have the weight vector and something which is telling you how much of a step to take for the weight vector, which doesn't depend on the weight vector at all. And this is because of the bootstrapping here. So by rearranging this, you can write it in terms of this vector B and this matrix A, where again, we're considering the case where the process has converged. So everything is in the sort of the steady state distribution. There's some expected value for the feature vector, and there's some expected value, for this quantity, which is the reward you would experience when you have a particular feature vector. And then, because you can write the update like this, the statement is that, if this is converged, then the expected step change for this should be 0. And in order for this expected step to be 0, it means that, this quantity is 0. And then because of how this is written, you can write this whole thing in terms of, some function of A and B, where we can come up with this, formula for what the parameters are at the TD fixed point. And then there's this, that there is a proof that, shows the conditions under which, well, first of all, that there's 2 proofs in the chapter. One of which is skipped, but I think you can find it in some references in the footnotes, which is that whatever this TD fixed point is within some bound of the minimum value error. But this bound is kind of worthless because like let's say gamma was 1, which is pretty common. Then this fraction blows up to infinity. So you're saying that the value error of the TD fixed point is within some infinite bound of the minimum value error, which isn't very useful. But practically we can check a lot of the TD fixed point errors and see what they actually are practically. The other proof was that this technique actually converges at all. And that, um, I don't think we didn't, I mean, it's a little bit technical and it involves, I mean, first of all, like you have to use this on policy distribution and show that it actually exists. So like this whole proof and these techniques don't work unless there is some like steady state distribution. And we'll see in later chapters, there are examples of these policies and MDPs where um, this distribution doesn't exist. And it's sort of related to this property of the MDP being ergodic, where you sort of have this randomization of which states are visited. If you have any kind of like deterministic sequence of visiting states or getting rewards in the MDP, it will violate this property. But you know, if you're interested in reading why this semi-gradient technique converges at all in the linear case, you can read this section. I mean, I think I have it reproduced in my notes too, but I won't go over it um, for now. But the point is that when we're using this the TD method, we're sort of on shaky theoretical ground with whether this should converge or not. And this shows sort of what the TD fixed point is in the case of the random walk example and in the case of state aggregation. We can see that clearly, you know, what this converges to. And I have, this has got a little squashed. Let me see if I make this wider. Because this, on my chart, um, yeah, okay, we'll start this a little squash, but you can see in the orange line is the TD estimate. And then, you know, this green line is the true value estimate. And the stepped blue line is the Monte Carlo estimate. This is after, I mean, this has gone long enough. So here, this is showing the value error for both techniques over time. And you can see like after, you know, this is quite a lot of episodes, 25,000 episodes, but, you know, both techniques have converged. It also is affected by the learning rate. So you could say like maybe the learning rate I picked is bad. I mean, if I make this larger, then, you know, or like I could change it pretty dramatically and it won't really affect the outcome too much. I mean, so this obviously like this is converging really slowly. I'd have to go out to way more episodes to see what happens here. But the reason why, you know, this is sort of independent of learning rate, and you wouldn't necessarily expect these to converge to the same value. And in this case, like clearly they are not converging to the same value. At least in the case of state aggregation. This isn't to say that this like can never work or that it will never converge to the correct value because right we have this proof of this bound, but like you know this error could be zero depending on what combination of techniques. It's just that it's not guaranteed to be zero in any case. So you're sort of in a situation where you have to empirically check what happens. So we can empirically check it for the random walk, and we can see that for state aggregation, there is quite a bit of a difference here, or this is the root mean squared value error. And you can see this is about like double the error of this, at least, you know, weighted by the on policy distribution. So, yeah, I mean, first of all, does that make sense to people? Like the difference between the minimum value error and how the TD fixed point is not necessarily the same as that?
I'm maybe having a little bit
Yeah.
difficulty understanding where the function is that actually does the reinforcement learning on this. So like when they sum up all these attributes, like how does it reinforce that decision? I guess I was a little bit confused on that.
Well, I didn't go over it this time, but these are all the I mean the actual um learning function here is either going to be um I'm distinguishing the gradient Monte Carlo algorithm from the semi-gradient TD. In gradient Monte Carlo, I mean this gradient step is what is doing the learning. It's updating the parameters of the approximator. And in the case of a linear technique, right, the value approximation is just the inner product of the feature vector and the weight vector.
So
For
what
state
if it gets
aggregate,
within that gradient? Like, how does it kind of pull out of that? Would that just be because of the Monte Carlo method itself, kind of thing, or
well, it's moving the values closer to the true values, which are given by this G. The G is the true return observed in the episode. So that is like the target value here. In the case of semi-gradient TD0, the target value is this bootstrap target value where it uses I mean, it's using the definition of the discounted return, but when it's converged, the true value of G should equal the immediate reward plus the discounted true value at the next step, if this value is correct.
okay?
But right here, I mean, this chapter is not concerned with, I mean, this problem doesn't even have a policy, right? This is a random walk. So, so far, these techniques are only concerned with estimating the state values of the random walk, which is just sort of an approximation of when you're in a given state, what is the probability of terminating either, to the right or to the left, where terminating to the right is a higher value. But yeah, chapter 10, which we'll get to in a little bit, is where we then try to optimize the policy, which in this problem, policy optimization has no meaning because, right, there is no policy to optimize. There's no actions to take. The the state will just randomly change to the right or to the left on each step. But yeah, this is the problem set up with a random walk from before. I don't want to go back over it too much because it's just this toy problem to test these different approximation techniques. So then, we had talked about these order techniques where we, like, let's say we have, this is the case of having a state with like two numerical values, and then we have a way of combining them. Like in this case, these are producing polynomial features where we're just combining, products of the state values. In the case of the random walk, there is just a single state value, right? It's just which state we're in from 1 to 1,000. So for that case, we just have these are like the polynomial features. We don't have to actually combine any of the state values. So what this is saying is that like if you're in, state 800 and we were to use five polynomial order features, then we would have a vector of length 5 where the five values would be given by the value of the polynomial um, for each of the polynomials at this state value. So this is just another way to construct feature vectors, but it's not necessarily a good one. In fact, these polynomial features are quite bad for producing good general results. So this is showing, again, the result of using the polynomial features. Um, Learning this is, again, like for the same number of episodes, the 25,000. This is showing the value error over time. And you could see it definitely has trouble at the edges. This is for features of 5. It should, like if I increase the number of order features, it should have more approximation power. But at the same time, it may also need like additional episodes to learn. In this case, you can see it's basically the more order features I had, the more rapid changes the polynomials would be able to capture. So you can see, this function doesn't actually need that kind of granularity in the value changing. But you could see that one thing that's different from the previous case is that for the polynomial features, the TD error is not really any worse than the Monte Carlo error. And that's because I could, like, the Monte Carlo error, if I run it long enough with a small enough learning rate, it should, converge to the true minimum value error. But the problem is that convergence rate could be extremely slow. And if you have these polynomial techniques, when you change the weights um, for the polynomial method, these, like, the shape of these polynomial functions end up making one state affect states like potentially very far away from it. So, like, if we change the weight like on this function, like every one of these weight changes will in general affect all of the states. So that makes the Monte Carlo technique take a very long time to converge. And there is some advantage in the TD technique because the TD technique, remember, uses more information about the state values immediately. So it will like apply these corrections, whereas for Monte Carlo sampling, we have to wait until we have enough samples for each individual state. And that was something we saw with the tabular techniques too, that sometimes the TD method can converge faster. So even though you wouldn't expect the TD fixed point to be better than the Monte Carlo one, you could see here like even this is already a lot lower than the value error of the TD fixed point for state aggregation, and we're not even using a good set of basis functions. Like these polynomial basis functions are not great. Now, another much better basis functions usually are these Fourier basis functions where in one dimension they would look like this, in two dimensions like this, but they're just these cosine functions where the higher the order, the more, the higher the frequency of the function, and you can capture more fine detail of the value changing over time. And also, we know from, Fourier analysis that we can reconstruct any arbitrary function from a large enough sum of these Fourier features. Now, the required number of Fourier features could be extremely large, which would mean that if we only pick like 5 of them, we may not be able to converge. You can see here, this is using just 5 of them. And again, both techniques are converging to pretty low errors. This is also over a much smaller number of episodes. This is only 10,000 episodes. And this has already converged, at least to the lowest error we've seen so far. Again, the Fourier features, like the polynomial features, if you change any one of them, it will affect, all of the states in some way. So the TD method is actually also converging somewhat faster. If you play around with these learning rates, you can get, um, you know, different results and how fast it converges, but you don't really see much of a difference in one method having an advantage over another. The TD method is sort of more stable, and you could see the learning rate I'm using is larger, and it looks like, the Monte Carlo method is even noisier, even with a much smaller learning rate. So this doesn't even need really more than 5 features, but I could certainly make it higher. Like I could go all the way to like 50 features, um, which is certainly probably overkill for this problem. You could see um, the results aren't really improved because this probably needs lower learning rates and more episodes to converge. And remember, like the more features I add, the longer the feature vectors. So also the more parameters there are. And the more parameters there are in general, you need more data to update all of them because you're sort of, diluting the value of each sample across more parameters. So, you could see this has more approximation power, but it also probably needs more data. And since we already know the true value is this mostly straight line looking thing, we don't need this many features. If I made only one feature would be an extreme case where, you know, this clearly doesn't have enough features. I think this is probably it's not possible because because the features look like this sort of, and I'm also mapping the states into this range from 0 to 1, so there's some consistency in computing the features. And yeah, obviously one Fourier feature probably isn't enough. Although, this is still as good of a value error estimate as we had from state aggregation. So, I mean, even one feature is not too bad, the Fourier method. And then, you could see when it starts making a bigger difference. But I think in the book, they sort of start out with five. But every time I run this, it's redoing the problem with new samples. And you can see that, the TD method is pretty consistently stable even at these higher learning rates. And then finally, they had talked about these coarse coding methods where we sort of have a set of overlapping regions, sort of like state aggregation. But then in state aggregation, any given state, like you wouldn't have any overlap. So this feature vector would just be a one hot vector. Whereas in this case, depending on how much overlap we have more feature vectors. This is extended into the tile coding technique where there's this picture in the book of tile coding where you sort of set up a number of grids that overlay each other. And then for any given state, it will be in a particular tile in these different layers. So if you have like four layers for each state that you pick, you have to identify which tiles it's in. Um, and that would be like the number of active features there are. And this is a way to do this coarse coding, but there's this picture here shows in the one-dimensional case, if I have a tile that's like a tenth of the total size, so that would mean that each of these squares, each direction, the size in each direction is one tenth of the total size of the state space. And then this is like the number of tiling, so the number of these layers that are overlaid. And then this is showing for the random walk problem, um, what are the active features for every state. So this is sort of like a visual representation of each feature vector, and the number of active states should match the number of tilings. And as you move across the state space, you just get different tilings active. Each one of these tilings is sort of like what you would get for state aggregation, where you just have a single step up. But here, because they're overlapping, you can see as we move across the state space, different tiles get active at different times. So this has more approximation power from the overlapping features. And then again, this is showing tile coding. This is with like here. So if I make this like one tiling, then you could see this will now match what the state aggregation picture was. Although you could see clearly, like with these learning rates, this is not converged yet. Um, and this needs to either run for more episodes or with a higher learning rate. I had the learning rate turned down because I had this with more tilings. In general, the more tilings, the larger the feature vectors, the smaller the learning rate has to be. You can sort of, there's a heuristic in the book about selecting the learning rate approximately. And you can see also with tile coding, because again, like as we change the weights on the different, like the different tiling components, this also has a lot of like states affecting a lot of nearby states, which is a reason why the TD method converges faster. And also just the way this is, it just looks like a lot of little steps because that's sort of the type of approximation that the tilings produce. And, especially another place where the value approximation is struggling is at the edges, which is also what we'd expect again, because remember these features on the edge have the smallest weight to them in the value error with the on policy distribution. But you could see that like, especially in this region, this is, hugging the true value line very closely. So, even though we had this previous discussion of the TD fixed point not necessarily being the correct answer, you can see like empirically with at least all of these other techniques other than state aggregation, that the TD method still manages to do pretty well, which is, sort of the main reason why it's introduced in this chapter, even though the math is sort of not, it's not that rigorous. But it still ends up working out empirically if you test it. So yeah. So that's sort of an overview of the different feature vectors. And one of the reasons I was going over these linear methods again is because we had this comparison between the update, when we do the Monte Carlo sampling, which was where this UT is G, and then the TD method where it's instead this bootstrap target. And then this writing it in this way with this vector matrix formula, it was a way to show how the TD fixed point is not necessarily the same as the minimum value error. But because of this relationship that you can write down, um, there is this other technique that you could imagine doing. Least squares TD basically takes the existing data that we've collected from um, from the steps that have been taken in the environment, and it attempts to compute the value of this matrix and this vector with an expected value. And the expected value is computed with the data collected so far. And then instead of doing the gradient steps, like we had described, it just solves for the parameters directly with this matrix formula. We have to take the inverse of the A matrix. Remember, the A matrix is this expected value of the relationship between the feature vector at the step we're on and the feature vector at the subsequent step. And it turns out there's this Sherman-Morrison formula, which allows us to, rewrite this computation of the A matrix. Actually, I'm not sure which. Okay, so this identity, okay. So this step from here to here is known as the Sherman-Morrison formula. This step here is just using the definition of A from here, where you notice like to compute, this is a way to compute the expected value of A, where we take, we're just taking this sum. I mean, technically we should divide by the number of elements, but it turns out that constant factor is not really important here. But, we're basically just taking a sum of all of these things across all the time steps that have been observed so far. Same with the B vector. Right, we're just adding up. This is just the easiest way to take the expected value of B. So then because this is a sum of this over time, we can observe that the value of the A matrix at any step t is just, the value of the A matrix at the previous time step plus whatever the new update is. So that's what this is showing. And then with some, linear algebra, you can end up rewriting this in this way so that the entire formula is just some function. So instead of actually recomputing the inverse at every step, we can just use the previous value of the inverse. And then we have to compute these vector and matrix products using the previous and the new feature vector. So this is sort of the pseudocode for implementing this, where we're sort of going to keep a running update of these different quantities. We have a running update of our estimate of the B vector of the A matrix, and then also this vector, yeah, this is just a convenience. This is like another intermediate quantity, which is used to simplify this expression here, right? V is just keeping track of A inverse times x times this, or yeah, this piece of it here. So we're keeping running updates of this. So actually in my, we go to, see, this implementation of least squares TD, it looks a little more complicated than the pseudocode. In here, probably because I think I keep track of one more intermediate result, but the whole purpose of all of these, so I have this running up running estimate for B, and there's a running estimate for A. I have this X3 quantity, which I keep track of also. Actually, this state representation. Oh yeah, so X3 is actually just the quantity inside of the parentheses here. The only purpose of doing all this is so that all of the math that occurs inside of the update loop, it doesn't have to, construct any vector. So all of these mul operations, these are either vector products or matrix vector products, and they end up just updating this argument with whatever, um, yeah, this this multiplication quantity is. And yeah, the B vector is updated in place as is stated here by the previous B vector, and then the current the current feature vector and the reward observed for the step. So because again, this technique, it only has meaning for a linear approximation, right? So these x vectors are all whatever the feature representation is at this state. And then, so basically what has to be defined to use this technique is the same thing that has to be defined when we do the linear Monte Carlo gradient or the semi-gradient TD, where we have to have some function that updates the state representation. And luckily, that's already been defined for all of these techniques. Like we can go back to, well, the easiest one to see is the state aggregation one. Actually, in state aggregation, we don't even um, update the feature vector because you don't actually need that to compute the gradient. So maybe I'll show here for the linear method. Yeah, we had for the polynomial problem, the feature vector update. Yeah, there's this function that calculates the polynomial feature. And then, yeah, for each index. And then it's updated here. But again, in order to apply like all the linear techniques, we already had the feature vector update function defined. And that is, again, what's going to be passed into least squares TD. So, like, let's say we want to apply this technique to state aggregation like we had before. So again, we need to make the feature vector update where to update, this feature vector, we can't do the shortcut we did before with the gradient update because here, the way this technique works, we actually need to have all these vectors and matrices explicitly stated. So it's pretty simple. In state aggregation, we just have this function that assigns a state to a group, which in the case of the random walk is just this like rounding function. It's right, like in one dimension. Each of these steps is just where the group cutoff is. And then we just set all the other features to 0. And we set the representation at the group assignment to 1. And then we can see, what this technique looks like. And it looks like, it did before. where here, I'll show the graph here, where this is showing, remember what the TD result was on state aggregation. You get the same kind of result. Again, it doesn't look that great. Like as in the TD fixed point is pretty, far away from the true value. We can at least see the least squared implementation is doing what we expect. And to see the difference between this technique and the semi-gradient technique, this is showing what the error was for each episode. And the main difference with the least squares technique is that it's a lot less noisy. In the long run, you wouldn't expect, the converged value to be much different. It could be affected a little bit by this value of epsilon, which it was shown in the algorithm here. There's this value of epsilon in the pseudocode. Yeah, which is what we initialize the matrix to. This is just to make sure that there's nothing like ill conditioned when we start doing the updates. And just to show you, like, it's also another point in the book that even though the TD technique, there's no step size we have to use. There's no step size alpha because we're just doing all these updates. Like technically, these expected values are being computed by taking averages for all the steps observed. So it would be like as if we did the previous techniques, but instead of using a constant step size, we were using like the true average technique where, effectively the step size is just 1 over n, where n is the number of samples that we've had so far. So it's a little bit of misleading to say that this technique doesn't have like a step size parameter you have to worry about, because if you were to use this where the policy is changing, you would probably want to change like this update to be like some kind of constant step size averaging update where the older values decay away, and then you would have the step size again. Also, we have this epsilon, which is needed anyway to make sure that the technique converges. And the epsilon value can affect the answer. Like if I set it to 0, so we imagine like we don't really need to use it. Now you could see the least squares TD it doesn't even appear because the values are all like not real numbers. And then if I make it, let's say like really small, so it's like, almost 0. Yeah, so this is still like also not even large enough to have the technique converge. So here you could see, I made the value of epsilon way too small, and least squares TD isn't even really converging. And then if I make it too large, well, in this case, you know, even this isn't too large, and this is a pretty large value. So I think if you sort of look at this and experiment with different values of epsilon, you'll see that it's pretty stable and consistent as long as you pick epsilon small enough. I assume if I make it here, let's say if I make it some ridiculous value. Wow, okay, so even making it a value of like 10, where it's supposed to be a small parameter, is still not, I mean, it's obviously not converging as well. You could see you have to make the value pretty large for it to have any problems. Here, so I'll just go back to setting it to some normal value. And one of the advantages of this technique is you would expect it to be a lot less noisy because we're not taking gradient steps. We're sort of incorporating, I mean, every single update to the parameter vector is using all of the previous information that was collected, because all that previous information is embedded in the A matrix and the B vector. Now, the downside is that we do have to perform these updates, which involve, some matrix vector products, and they are a lot more computationally intensive than the gradient update. At least, I mean, one of the main problems is we do have to take at least one of these matrix vector products. And remember, in the case of linear gradient methods, the gradient update in here, like this was just one inner product. And then again, like the gradient was just the feature vector. So we basically only have to take one inner product to do this gradient step. And for least squares TD, we have to do a lot more computation. And you do end up getting faster convergence and a lot less noise. But if you run the semi-gradient technique long enough with a small enough learning rate, you should end up getting the same answer. So this is just like the one place where this technique might have an advantage is if you really have like very limited data. So you don't have, or like you're restricted to a number of episodes where you can't like allow it enough time to converge. And, at least you could see for very like short numbers of episodes. Oh, sorry. Especially in the early phases, like this converges really nicely compared to, this method where if I set the learning rate high enough for this to converge better in the early phases, it would just be, even noisier than it already is. This is showing here. Try to make this a little bigger. So as long as you define those feature vector updates, you can apply this least squares TD technique. Uh, yeah, to any of the previous methods we had before. So this is like polynomial Fourier tile coding. You can see in all the cases, eventually you'd expect the gradient technique to converge to the same thing. But again, it's noisier. It could take longer. It could take longer in terms of number of episodes. It will not necessarily take longer in terms of the execution time because each of these least squares TD updates is much slower and it scales quadratically with the size of the feature vectors. Um, yeah. So even in the case of state aggregation, like this would be the number of groups. We'll scale quadratically with the number of groups. Because yeah, eventually we do have to compute these matrix vector products. So for this, even for this small number of states, you can see, it's still like taking 5 times longer to do the least squares TD for the same number of steps. So if you're constrained by execution time, probably the semi-gradient method is better. If you're constrained by data and you have all the time in the world, the least squares TD will, make better use um, in the limited data case, and it won't be as affected by noise. You can see that more when we start using, other features like the Fourier features that, yeah, the least squares technique um, converges quite quickly. Like this is even, this is only out to 1,000 episodes. Remember, earlier we were showing up to like 50,000 episodes um, for state aggregation. So, yeah, okay. Are there any questions about how least squares TD works or comparing it to the semi-gradient method?
I have a quick question.
Mm-hmm.
So, I'm a little bit couldn't follow. We were talking about the state aggregation. That's why we have the step shape
Mm-hmm.
estimated value, but somehow some figures doesn't have step shape state values.
Yeah, like you mean for
What
like the Fourier
this one?
basis?
Yeah. So is that because we are not?
Well, it's
Mm,
because we're using different, right? Like, so for the Fourier approximation, the
mm,
feature vectors are constructed differently. And
not aggregating or
yeah, not
because of the
aggregating.
function.
Yeah, actually, so I'll go back to the polynomial. And so this is showing
Oh.
5 polynomial features. So
Mm-hmm.
basically, if you want to construct the feature vector of like state
Uh-huh.
500, you
Uh-huh.
would evaluate, well, first of all, I'm showing this from 1 to 1,000 for convenience, but the way these all work is they end up mapping all the state values from 0 to 1. So this is sort of showing like all the polynomial features. It's the same thing here for the Fourier features. This is all from evaluated from 0 to 1. So everything gets normalized from
Mm-hmm.
0 to 1. And then you take this as like zero point 0.5, right? It's in the middle. And then this feature vector is going to have 1, 2, 3, 4, 5, 6 values in it. And the
Mm-hmm.
values are just the value of these curves here. In the case of Fourier, it would be like this value, this value, this value, and this value.
Mm-hmm.
So you're evaluating these
And
functions
and
and mhm.
mhm. So these values that is representing the features are fixed at
Yeah.
the beginning,
Oh, well, no, those are fixed the whole time.
the whole time.
So though that's
And
what's called the state representation. So every
mhm,
state, depending on, so we have to set this up and pick how to do it, but we take a state and we map the state to the state representation. So in
mhm,
the
mhm,
case of here, I'll do like it's probably easier to look at the tile coding. So in
mhm,
tile coding, right, we don't have to worry
yeah,
about these functions. All we do is we have to pick like which tile is it in. So
mhm,
like this is showing which features are active for each state. So these are the state representations for this setup of tile coding,
mhm,
and these stay the same the whole time. Now, the approximation function is going to be a list of parameters where there's one parameter for every feature. And then when we compute the approximation, here does this show it? Yeah, for linear methods, each approximate value is just the inner product of the
mhm, yep,
xs. This is fixed. It's fixed for every state. These are what's changing.
yep,
And this inner product computes the approximate value. So like you could see, because this technique ends up like turning on and off tiles in these steps, we also have this step-like um, structure to the approximation. But in the case of like the Fourier basis, like I'll make it so you could see like one feature, right? This function is just looking like a constant times like the first Fourier feature,
mhm.
right? It just looks like a cosine function, which has been stretched
Oh, I see.
to minimize the value error. This is the best it can do for only one feature, right? All it
Mhm.
can do is select, you know, what to multiply this by to fit the value function.
I see, I see.
And then
Cool.
when as you add more features, you're basically just creating like a Fourier approximation of the value function, which as you add more features, eventually it can exactly approximate the value function. If you know, in the limit of infinite features. But yeah, I mean, this is just an arbitrary choice. Like you could also construct the features randomly. Oh no, actually,
Yeah.
well, you can't do it completely randomly because like if you have a state S, it always has to produce the same feature vector for that state
Mhm.
S. And you know, good features are sort of determined by like ideally, like let's say that two states are similar in value. Ideally, their feature vectors would also be similar. But of course, in an arbitrary problem, the whole reason you're trying to solve it is you don't know what states are, you know, should have close values. But for this, we could see that obviously, like the reason why state aggregation works pretty well for this problem is because of the shape of the value function. It's like states that are
Mhm. Mhm.
close together in their number also have a
Yeah.
similar value.
Yeah.
But for a different problem, it wouldn't be the case.
I see. So that means for a different problem, the Monte Carlo and TD0 might have different performance.
Oh, that's true. And also which feature vectors are good would also be different.
I see.
But I mean, tile coding is pretty flexible. The other thing I showed it last time, but you can also use a nonlinear technique. So sorry, this implementation is showing like a neural network technique. So here you could choose the number of layers and the layer size, and this is using like an Anch activation function. And this is as I make the layer size bigger, this approximation here, you don't have to like define these. You do have to convert. You do need a state representation which is compatible with the network. In this case, it's literally just the integer value of the state. And then that's, because this isn't a linear technique, I can choose like a large layer size. And basically the network will learn like embedded in these parameters will be like some sort of feature vector representation, but it's not something which is defined ahead of time.
Mm-hmm.
And this also in theory like can approximate any function, but this is also a case where the TD method is doing better. It's converging more stably at a higher learning rate. And this is also, may also need in general like more episodes before it converges well. Yeah, like probably more episodes and probably, I mean, once you start going into nonlinear techniques, now we've also lost whatever sort of shaky guarantees we had for the linear techniques. So now we're even more in a sort of case of empirically testing things. Like here, there's not even a guarantee that this will converge to the minimum value error, even in the gradient Monte Carlo technique, which will converge in the linear case, because this, not like this nonlinear optimization could get stuck in a local optima. But
Yeah.
yeah. Does that make sense?
Yeah, definitely.
Okay. So everything we discussed, these are all parametric methods, meaning like they have these parameters, whether in the linear case, it's just a parameter vector, which matches the size of the feature vectors. In the nonlinear case, the parameters will be a different format entirely, but there's still a list of parameters that are updated. There's this other technique mentioned, which they don't actually show any results of it in the book. They just sort of mention it briefly, but this memory and kernel method. But I think it's worth looking at because sometimes the results you get from it are a little more straightforward and easier to understand and implement. So in the memory-based method, there's sort of two steps. And also, this really only makes sense in the Monte Carlo case, which is another weakness. Sometimes the Monte Carlo, like sometimes the techniques that only work in Monte Carlo just aren't suitable for learning in the future because we don't have a guarantee that we're going to terminate an episode. And the problem itself could be continuing, meaning like there are no episodes to begin with. So keeping that in mind, let's say we do have a problem where we can make sure that episodes terminate, and we can then here, let me see, how do I want to, okay, so the two parts of using this technique come first, we have to sort of build a memory of data that we collect from running a policy. So what this is doing here is we have this lookup of state values. Yeah, and I think it's using this. So the reason why what this is saying is we have a lookup of state values where for each state we have a record of the number of times a state has been visited and then the average value that we've observed. And this is the average value as computed with Monte Carlo sampling, right? So we're going to run, in this case, like we have an episode that's been run to termination. We have a list of states and rewards that were observed for that episode. You can actually do this in different ways. Here I'm doing it, I'm not using alpha. What this is computing here, this is updating the average of the state value, and it's using n, and that's because n is keeping track of how many times, right? It's incremented by 1 every time we visit a state. So the values that are stored in this memory are really just the average state values that have been observed. And here, there's also a version of this that increments it with a constant learning rate. But since we're just explicitly doing everything episodically here, it makes sense if the policy isn't changing to just compute like the true average of the state value. So then what this does is, let's say, the reason why there's 2 of these is because I have a version of this that works for the Markov reward process, which is like the random walk where there's no actions. It's just the dynamics are just the same on every step. But what happens is we run episodes. So then we have, the collected data from the episode. And then we update the state value memory using the result of running the episode. So this is, this is just written this way so that, one of the problems with running episodes is you have to keep collecting the lists of the states that are visited. And it's helpful if you can reuse the list. So here, this is just written this way so that once you collect a list of a certain length, it will just reuse that list and only, increment it up to the point where there's relevant data. So at the end of running this process, we should have this list of the states that were visited and the associated values. And this is sort of, you could imagine doing this, like dispense with all of the gradient techniques and everything we talked about with, minimizing the value error. This is a totally different approach. There's also no parameters here. So then, once we build a memory, the idea we're going to use is this kernel-based function approximation, where we have a kernel function, which all it does is it tells you for a given state that you care about, in this case, like the state S, and we have, in this case, D is our like memory that we have with the stored examples. So it says, let's say that we look at the memory, right? And in the memory, we're going to have like, a bunch of states that we can look at. And what K does is it tells you for every state, how much should you weight the value of that state compared to all of the others. And then G is just the approximation stored in the memory for that state. So we're going to compute a weighted sum through the whole memory of a state. And the kernel function just tells you, how much importance this state value in memory has on the state that we actually care about. And the kernel function really could be anything. One common use of a kernel function, for example, could be some sort of distance metric. Like in the case of the random walk, the states are just integer values. So this could just be like how close, like physically close is a state to another state. Now, because the random walk only has 1,000 states, the memory is actually going to have states that match exactly the state we care about. And in that case, the thing that you would do is just take the state value for the matching state, right? Because we already have an estimate that matches. And then we're sort of back into a tabular case. The point of this example, though, is like 1,000 is just an arbitrary number. Like we sort of want to take the limit to where the number of states goes to infinity so that we wouldn't really expect the memory to have any exact matching state. And then the kernel function would actually need to compute that. Now, it turns out that let's say that we have some feature vectors like we had previously, then if we pick the kernel function to just be the inner product of the two feature vectors, then that is equivalent to all of the techniques that we've done previously, assuming that we, compute the state values with the same averaging we would do before. And of course, this only makes sense for the Monte Carlo technique. But the sort of intuitive meaning of this is that if we have a linear method with feature vectors, the importance of a value in memory to a query state is just how similar the feature vectors are. Because this inner product is going to be higher the more overlap there is with the feature vectors. So here, I'll just show an example. So here, if I run the random walk, like this is running it for a lot, but this is like more episodes than I've done in any previous example. But here, I'm building a memory over 100,000 episodes. And this doesn't, one of the nice things about this technique is that it doesn't actually take very long to assemble this memory. And here what I'm showing is actually like what is in the memory, right? So this is showing like for every state, like what the memory value is. And like already you can see that like this is already basically like showing what the value function is. Like, and because I've done so many episodes and there's so few states, the memory actually has a value estimate for every state. So in a sense, we're already done. But the point of this technique is in the case where the memory wouldn't have a value for every state, which is why we would have to use the kernel function. So the other nice thing about this is once you have a memory, you can then just see what different value approximations are by applying different kernel functions, right? We don't have to rebuild the memory. We can actually use the same memory and just try different kernel functions. So here I'm using a distance approximation, where here, since the states are just these numbers, here I'm just using the squared difference between the states as like a sort of distance metric. And then the idea is that I take the inverse of that. So basically states that are closer will have a higher weight. And also to normalize this, right? Like sort of embedded in this is the fact that the kernel function should sort of produce normalized values because we're taking this average across G. So practically what you sort of do is you evaluate the kernel function at every state, and then at the end you just divide by the sum of all these k's across everything in the memory. So that's what I'm doing here. Also, I have this value of epsilon here, which is to sort of simulate the case where we don't actually have the exact same state. If the states match exactly, this is 0, the inverse is infinity, and we can't do this. What you would do in that case is actually just you wouldn't care about the distance metric. You would just find the matching state and use that. But using this value of epsilon, you could sort of see, it's getting rid of the singularity at that case. So now it's not only going to use the state value that matches, it's also going to use all the states with decreasing weight as we go farther away. And this is showing this applied with this particular here. So this is showing with this value of epsilon. So if I make the value of epsilon 0, it's not going to work in that case. But if I make it arbitrarily small, then it's just going to weight like the state that matches in memory to be the highest, effectively just using that value. And you can see now this is like pretty noisy. It's matching the noise of what is in the memory itself. But you can see like the error is still, of course, it's 100,000 episodes, so it's more data than before. But you can see even like evaluating this is very fast once we have the memory. So all told, like this technique is actually can be much faster than the parametric techniques. And then if I make this what I had before, where it's more like where now it's actually using it's weighting the values across more of the state space, depending on how close they are. And you can see like it's pretty much, this distance metric is very effective for this problem. And then this is showing, again, like I'm just making the kernel function here. So here, this is doing the same thing as before, state aggregation, but the kernel function for state aggregation is just checking if a state in the memory is in the same group as the query state. So then if it matches the query state, then we average those values. And these results should end up matching exactly what we had before with state aggregation, where each of these steps is just showing like, this is the average value of all of the states in the memory that were in this group. But this is doing it much more directly than the gradient method is doing, right? This is just like explicitly computing that. And once we have the memory, I don't actually have to rerun the problem anymore. I can actually just look at the same memory and apply a different aggregation to it. And you can see it'll just reevaluate the approximation function. And each one of these reevaluations is extremely fast. And as you'd expect, as I increase, the number of groups, this approximation is just getting better and better, or it's just getting more and more granular. But, this is a lot faster to reevaluate than doing the gradient technique all over again. Tile coding, kind of the same thing. Also, if I bring this down to, this is just showing the equivalence between tile coding and state aggregation. If you do tile coding with one tiling, right, you just get the same state aggregation. So here, as I increase the number of tilings, it's going to be similar to this, but a little bit more efficient than just adding more groups, because here the groups are actually overlapping. And yeah, you can change the tile size. But yeah, so that's the kernel technique. Also, another point about the kernel technique is to apply it, right, we have to compute the kernel function, which for linear methods is this inner product, right, of the two feature vectors. But if there's a faster way to compute this inner product, then you can just do that without constructing the feature vector. So I'll just show you for the tile coding, like this function, instead of actually updating the feature vector for tile coding, this is just getting, it's finding like what index would be active for tile coding for this particular state. And then it's just taking the sum of the feature vectors in the memory. So if I have like a list of all the memory states and their feature vectors, then I can very quickly take a new state, figure out what the kernel function weight is for that state without ever having to actually have a representation of its feature vector. So this is sort of like a way that you can shortcut what you would normally have to do with like least squares TD or the gradient methods. Because all we have to do is compute, this inner product. And in the case of tile coding, this inner product is only relevant where the features are non-zero, because the feature each feature value is either 0 or 1. So that's another reason why this can be evaluated very quickly. Here, as I keep adding more and more, like if you do like 100 tilings, you would expect at some point for this to take longer, but yes, like 100 tilings is taking longer, but like this would take a much longer amount of time to train. Like now the tilings there's so many that you can't even see the steps anymore. But this would take like a much longer period of time to train if you were to do this with a gradient technique. And, this memory, yeah, I mean, even like building the memory also didn't take very long. So yeah, again, this is what would be called a non-parametric method, because like the value function depends on the memory that we've collected, but that's it. There's no actual explicit parameters that are stored. Every time we want a value, we have to evaluate the kernel function here. So are there any questions about kernel techniques? Then I think I mentioned we'd go over, okay, wait, these two exercises. Also in the book, yeah, it might be, I think like some of the math in these examples is helpful, I think, for the understanding of the linear techniques. But let's see. So this exercise is saying it's sort of making a connection between the linear techniques and a neural network. So instead of having a full-blown neural network, you can just have a linear approximator where you apply this logit function to the output value, right? So you would have the inner product of the feature vector and the weight vector. And the reason why you would do this is because what this function does is it maps the entire, output line to a range from 0 to 1. And if you have a problem where like the true values that you're trying to approximate are just either 0 or 1, then this output function helps the approximation a lot because we're necessarily forcing the output to be in that range. So, let's say we have an approximation where we are applying this logistic function to the output. And the question is, what is the gradient update in this case? So if we go back to the original gradient update formula, right, we have the delta value here, and then we have to multiply that by the gradient of the approximation function. And in this case, v hat, instead of the inner product of the weight vector and the feature vector, is actually that quantity times f, like where f is this logistic function. So this is the definition of the logistic function, and it has some nice properties. One of the properties is that, well, for convenience, I'm going to say e to the negative x can be expressed in terms of the logistic function like this. This is just the algebra that does that. And this trick helps us actually write the derivative of the logistic function in terms of itself. So if we just take the derivative, explicitly with the chain rule, we get this term. And notice that this 1 plus e to the negative x to the negative 2, this is just the original logistic function squared. And then e to the negative x we can replace with this expression. So using those two pieces, right, this is all just so that I can express the derivative of f with f, and it's just f times 1 minus f. So then if we go back to this gradient expression here, we can end up just replacing that. So we have, the term inside here is just v hat. And then, right, this term here, like here, we're also using the chain rule that once you take the gradient of the inner part, you're just left with the feature vector. So here we have the expression, which is just the derivative of the logistic function, and then times the gradient of the linear portion of it. And this is the weight update you would have. Again, right, this 9.7 was using the squared error loss function, which is why we still have this form of it. But yeah, you end up getting this, yeah, this form of the gradient update. And to compare it to what we had before, I can actually read this. Yeah, so this was the gradient update. Sorry, in the linear case. Right here with a ut. And in the linear case, we have this very simple form where the outside here is just the feature vector. And here, instead of the feature vector, we actually have f evaluated at the inner product, and then 1 minus that times the feature vector. So the extra term here is just this term, which is the derivative of the logistic function. As a follow-up question, remember that so far for the value error, all of the formulas in this chapter are using this, right, squared error objective. I said this is sort of an arbitrary choice. Another option is to use the cross entropy loss, which would actually be more appropriate for a problem where the only outputs we're estimating are 0 or 1. This would be like if you have a game where the only outcome is a win or a loss. So then the value estimate is actually just the probability of winning. And an appropriate, error function comparing two probability distributions is actually the cross entropy loss. And this is showing what the cross entropy loss is for a single output. So in this case, y hat is our approximate value, and y is the true value. And this is the formula for the cross entropy loss. Remember, if we have a single output y, we're concerned with a case where y would either be 0 or 1, or true or false, win or loss. So really, the full loss function can be represented by these two curves, where the blue curve is showing if y is 0 or false, this is what the loss is. So the loss is 0 if we're correct, and then it blows up to infinity if the estimate is 1 or true, and it's symmetrically mirrored for the other case. So right, in the case of squared error loss, like if you outputted an estimate of 1 and the true value is 0, then this value would just be 1 as a loss. Whereas if these are really probabilities, that is as wrong as you can be with a probability output. So really the error should be much higher than that. And it should diverge as we sort of output like 100% probability, the wrong answer, then the error should go to infinity. So does that make sense to you? If you're not familiar with cross entropy loss, how this works? But this, in general, you can use this to just compare how different two probability distributions are. So if we use the cross entropy loss instead, I'm just going to write here what the cross entropy loss is for our approximation using the logistic function f, like we had before. And then we can go back, instead of this, we can go back to the more, actually, it's not even written in the book, but this formula, right? This is saying that the gradient update should really be, we should use the gradient of the full loss function. And this is the gradient with respect to the parameter vector, W. So right here, this has already been right? Like this has already been computed using the squared error loss. So here I'm just sticking the entire loss function into here and using what we already found out about the logistic loss. So this is just, here we have the log of the logistic function. So if you apply the chain rule to this, right, we just have to take 1 over the inside of the log times the derivative of the upper part. And we already had this form. So this reduces very nicely to just being 1 minus f. And similarly, the gradient of the log of 1 minus the logistic function is just minus f. And we also have to take, the gradient of whatever's inside, which in this case will be, right, this inner product of the parameter vector and the weight vector. And then if you go through this algebra, writing this down, a bunch of terms cancel out. And what you end up with, this is the final parameter update, actually looks almost the same as the original formula for the parameter update. The only difference is that the approximate value in here is the approximate value using the logistic function. But everything else is the same. So actually, if we use what's really the appropriate loss function for this, we have a pretty nice version of the gradient approximation technique that is suitable for problems with these probability distribution outputs. And all we have to do is apply the logistic function to the inner product output, and then everything else in the formula can remain the same, where we just have this simple feature vector left over for the gradient. Yeah, and whereas before right here, this v hat is this inner product, and now we're just applying the logistic output to it. So maybe I could also add an example in here maybe of, or maybe I could do the random walk example where I consider terminating to the right to be a success and to the left to be a loss, and maybe show the same techniques with the cross entropy loss. But yeah, I could maybe do that later. But are there any questions about these exercises? If not, I think I was maybe going to move on to part of chapter 10, but I think now it might be a little too late for that. So I guess for the next meeting, we can start on chapter 10, which is probably more interesting to everyone, which is the case of actually optimizing a policy. And we'll see that, we can actually end up reusing all the techniques from this chapter. Just this little preview. We're going to follow the same pattern as before, where we take action value estimates of everything instead of state value estimates. So instead of just having the state values in a problem where we have some sort of list of actions we can take, we're going to have a different approximation for every state action pair, or our function will compute a different value for every state action pair. And then we can follow the pattern we had before with this generalized policy iteration, where yeah, it's sort of an extension of the SARSA technique, where we start out with a policy that is random. Wait, do I have this here? Sorry, it's up here. We start out with a policy that is random, and then when we take actions in the environment, instead of using the fixed policy or no policy like we had here, we try to make the current action we're taking greedy, or epsilon greedy, with respect to the action values that we have so far, or the approximate action values we have using whatever the parameters are at the time. And everything else in this loop ends up looking the same as the TD value estimate. The difference is that the policy is always being updated with these action value estimates. And yeah, the problem, the example problem in this next chapter that we will spend most of the time on is this mountain car task. Sorry, where we have a car that's sort of spawned at the bottom of this valley. And if the car tries to just accelerate, it doesn't have enough power to leave as the slope gets steeper. Um, Eventually, it will fall backwards and then decelerate until it gets to some point here. And the reason why this is an interesting problem to try to solve, and also why the Monte Carlo techniques have a problem with this, is that if you just sort of take random actions or take the same action in this, you won't really ever end an episode. Even though this is an episodic task, the goal is to get to the right side. And here I'll just show a little preview here. So this is just showing the sort of the problem in, oh wait, sorry. This isn't exactly what I meant to show. It's the true problem. Oh yeah, sorry. So this is for this task, this is showing what happens to the position of the car over time if you just accelerate. And you can see it just oscillates back and forth in the trough. So clearly, this will actually never terminate. If this was some initial policy that you had started with, I mean, even this is showing the random policy, and even the random policy, this is after 1,000 steps. It's still oscillating. This is showing the phase space of the car in the trough, where this is showing the position and velocity at every point. So oscillating back and forth just looks like a circle in phase space. And this is like a bunch of sort of random stretched circles or ovals. And you can see it's just sort of moving randomly and it doesn't have much luck. It turns out if you run this long enough, the car will exit. 10,000 episodes in general, or sorry, 10,000 steps in general is not long enough for this to happen. Let's see, I'll try if I go to maybe 100,000. Yeah, so in 100,000 on step 18,069, this did manage to exit to the right. So that next time we'll go over, yeah, in this case, it took a little fewer steps. So actually, you could use Monte Carlo techniques with this problem.
Is that affected by the learning rate that you input for that?
There's no learning here. I'm just showing the random policy. So yeah. So eventually in this chapter, we'll apply all these techniques to learn the optimal policy for this task. But this is just showing why this task might be difficult to solve because, normally what we do is we start with a random policy and we collect data from the random policy. Let's say like if the random policy even like here after 32,000 steps, it did exit. But, the point is that a simple policy like this or the random policy is very uninformative for this task. And like the data from this is clearly not very useful because, the number of steps it's going to take to finish, and you have this attribution problem where you have no idea which thing you did across 32,000 steps that was actually useful. So we'll see that's why this is sort of used as an example where these SARSA techniques work well. And we can also try solving this with a bunch of the different, like these techniques, these linear methods, and even the nonlinear method. But again, to apply them, we have to create action value versions of them like we did in the tabular section of the book. And that's what I'll go over next time is how to form the action value implementation and then what the results look like for different techniques apply to this mountain car task. So does that sound good? Good to everyone? I won't. Yeah, to just leave that for next time. And were there any questions remaining from what we went over in chapter 9 or these exercises?
I guess on the mountain cart test here, if you added a second gradient, like went down on the hillside, I mean, could it still, I mean, I'm just trying to see how that would affect things.
A second, wait, what do you mean? Where?
Multiple potholes on the way up type of thing. Where you had to
Yeah,
like,
I mean, it would make the task harder for sure. I mean, at some
so
point, you would make the task impossible
yeah, that's true.
because the car. But yeah, I mean, this is just sort of a simple setup that still doesn't have an obvious solution. I mean, the solution, like you have to end up sort of building up momentum by going backwards to solve it. But exactly how you do that efficiently is the hard part about solving it. Yeah. But I was just showing, because chapter 9 is just like we're just forming these like value approximations. So I'm saying if you were to take the policy where you accelerate only, you just try to accelerate. And I showed that it just oscillates back and forth, right? Like that never terminates. So technically, the value of every state action pair is just negative infinity. For this task, the car just gets a reward of -1 every step. So the highest reward would be for getting to the goal the fastest.
So are you familiar with the hidden Markov models and how that can solve like combinatorial problems? So like for example, in this mountain car problem, you could have a combinatorial solution, right? If you started added certain potholes in here. So is it possible to keep track of, I mean, is that essentially what you would use your Markov model for? Or
Well, in this case, the mountain car task itself is a Markov process where every step, you update the position and velocity of the car like this, depending on what action you take. This is a deterministic problem, though, right? It's not like there's a deterministic um, output step. But are you asking about the setup of the problem itself or the solution technique?
I'm just
Because
saying for
like
like combinatorial problems, like some like solving a Rubik's cube, sometimes you have to have certain steps that must
combinative,
happen before other steps.
yeah, sure. I mean, these techniques are not limited. Like you could formulate a Rubik's cube problem as you know, like as a Markov decision process. Like you just have the the state of the cube is the state, and then every action you take of like some rotation just updates the state deterministically. I mean, that's another case where like the mountain car problem where you can't just like move randomly and solve the cube or like you can't just take the same action over and over and solve the cube. You have to sort of explore the space a lot. But like these techniques would approach solving it in the same way. Like all of the complexity about what steps have to occur before other steps would be contained in the state action values. Because like the state action values are what tell you, like for example, like let's say in this random walk example, you actually like had actions to take, like you could go right or left. Um, in that case, what this value function is showing is the value of the random policy. Like, right? Now, if you evaluate the values of the random policy, it becomes very obvious that values to the right are higher value than values to the left. So then whatever state you're in, if you could take an action that takes you into this state, you would prefer that over an action that takes you to this state. Now, this is like a trivial example, but it's the same exact solution technique where like if you had the Rubik's Cube, if this graph was like the state action values of a Rubik's Cube, then the way you solve it is you try to get accurate values by sampling, and then you try to update your actions so that your actions are moving you into higher value states. So like if a state is higher value, it means it's closer to the solution, like including all the complexity of the problem about like what all the, so like if you took a step that got you close to the solution, like superficially, like it looked almost solved, but then there were like a million more steps that had to happen to get the final part of the solution, that state wouldn't be a high value because it would, in reality, it's far away from the solution. So the whole point of the value function is it tells you like what states or like what actions and states are actually beneficial to be in. Because like the ultimate goal of this is to figure out the optimal action to take at every step. And this action value approach is to solve that problem by just taking actions that improve your value estimate. I mean, that only works if the value estimate is good, meaning it's like an accurate representation of how close you are to solving the problem. But that's also, right, the entire goal of these approximation techniques is to have good value estimates. And in this trivial problem, it's obvious to see that like ideally we want to be increasingly in states closer to the right. And in the case of the random walk, the states literally go from left to right. In the case of a Rubik's Cube, right, there's no obvious like spatial placement of the states, but that doesn't matter because you would end up just mapping the states into some feature vector like we do here. And then if, like the problem is the features might be bad. Like that's a good example of a case where knowing how to map the states is not really obvious. Maybe even one of the nonlinear techniques would work better for that because then you don't have to, worry about picking bad feature vectors. But still, the approach is to, sort of reduce the problem to one where we can just clearly see a direction towards which the state values are higher. And this problem is deterministic, but you could modify this problem to make it, stochastic. You could have randomized potholes where if the car passes over a pothole, it loses some amount of speed. And the position of the potholes could, not be known ahead of time or even be random at every step. So then, you would get a different solution. The solution would probably be harder to find. And yeah, it would be different than this deterministic version of the problem.
Thanks, Jason, for going over all this. That's helpful.
Yeah, sure. So are there any more questions or requests for next time? Or I mean, would it be helpful to see what I mentioned before, or like this like cross entropy loss version of the approximation?
That was pretty obviously
Right.
the case. Maybe I'm misunderstanding what you're saying.
Oh no, just I mean, we didn't all of the problems in chapter 9 were using the squared loss, like the mean squared error loss instead of the cross entropy loss. So the cross entropy loss is more appropriate for tasks where the rewards would be either like 0 or 1, Like in fact, you could even use it for the mountain car as I mean, no, you can't use it for the mountain car task because it actually never terminates unless you hit the goal. It's really most appropriate for things like games where the game will end like regardless of what you do, and the outcome will either be a win or a loss. And then this version of the gradient update is, more appropriate than trying to use the squared error. It's the same kind of thing with supervised learning, where if you're trying to train a classifier and you're using like squared error loss, you can use that to train the classifier where you're trying to make, the label output match the target output in terms of squared error. But really, because they're both probability distributions, it's better to use the cross entropy loss for the supervised learning because that will more properly um, force, the output distribution of the model to match the target distribution.
So from a practical example, are most people just trying to replace most of these function calls with just uh, a standard neural network? So rather than using, all these equations, you could just kind of replace it with a neural network.
Well, I mean, let's say you do so like this, you can use a neural network to approximate the value function. Like here, that's what I'm doing here. But like the gradient update, you go back to like if you stick with just the original technique, right here, like we're like this gradient then is just going to be the gradient of the neural network, right? Like this v hat would be the neural network, but you still, I mean, even like when you train a neural network, even with supervised learning, you still do these gradient updates.
So in the case that the neural network has a complex gradient, is that like what's that going to look like? Is that so that's going to be that output of that function is going to be a complex gradient there? So this is a nonlinear gradient, right?
It doesn't matter. So, right, like this, so this W in the case of a neural network, these are the parameters of the neural network, whatever they are. This gradient will produce something that is the same shape as this, right?
Oh.
This in the bracket, this is a constant number, right? Because this v hat is the value approximation. This is a single number. So this whole thing is one number. This is the same shape as this. So the gradient just gives you, for every parameter, a way to update that parameter. But yes, if it's linear, this is just a vector. If it's a neural network, this could be a list of tensors or, something like that. Like it's still a list of numbers, right? But there's a list of values and a corresponding gradient that will tell you how to update that value. But this is the same for doing supervised learning. I mean, whatever the neural network, however many layers, all this stuff, you just use the chain rule, you compute the gradient, and you always just end up with a gradient value for every parameter.
So on that car problem, is there like a minimum size of the neural network that could be, I mean, could you estimate that beforehand, how large that neural network has to be in terms of, number of connections prior
Yeah,
to,
to solve it.
yeah.
Well, that is I mean, even with
Because it looked like
these
it took like
techniques,
8,000 tries. That sounds like a lot of tries.
8,000, wait, what do you mean 8,000 tries?
You said it took like 10,000 tries just to solve it. So that
Oh, no, that wasn't solving. Oh, you mean, okay, sorry. So here, going back here, this is saying, so by the way, like this isn't solving anything. This is, if you have the random, oh, sorry, wait, let me go down here. If you have, the random policy, right? This is saying that like if you just take random actions, like this didn't even, right? This is 10,000 steps and it didn't, it, right? This is about whether it reached the goal to the right. Because in order, I'm just talking about running episodes. So an episode in the mountain car task is the car starts here somewhere. And then if it goes too far to the left, it just gets reset in the bottom. Oh, no, sorry. That's not true. If it moves too far to the left, it just gets reset at zero velocity on the left. But the only way the episode can terminate is if it reaches the goal, right? So the reward for the episode will be negative the number of steps to the goal. So if you have the random policy and you try to run an episode and you give it, like you hope the episode will terminate in some reasonable time. But for this particular problem, if you give it a random policy, the episode may not terminate for, 100,000 steps. So I'm just saying that poses a major problem for a Monte Carlo technique, where in order to start learning, you need to have at least one completed episode because the value, like we can't start to build value estimates until we have a completed episode, which is one of the limitations of the Monte Carlo techniques. But if this, like, if I move randomly, like, because you'd say, if you didn't know anything about reinforcement learning and you said, like, okay, I want to try to solve this problem, like, the sort of concept is, okay, let me just randomly move and see what happens. And you see, okay, after 11,000 steps, I reach the goal. Now, what Monte Carlo learning will do is it will take all of this mess of data and it will try to incrementally improve something so that the next time you try this, it will finish faster. In the case of approximation, that's not even guaranteed to be the case. But that's what the goal is. But as a person looking at this, like, yes, technically after 11,000 steps, we reach the goal, but I don't think you could look at this, set of data and say, oh, now I know how to solve the problem like efficiently. Like, that if you move randomly, you may by chance reach the goal in 10,000 steps, 30,000 steps, like whatever it is. But that's really all you know until you start doing additional learning. If you were starting out with this policy where you just accelerate, this will never reach the goal. But, like knowing how complicated your estimator has to be to solve this is not something that you can really do ahead of time. But when we go over chapter 10, I will show a number of sort of tests that you can do to get a sense of how elaborate the value function may need to be. Here in the book, this is showing as this is optimized what the value function looks like, what the state value function looks like for the position and velocity of the car. And you can sort of get a sense of, depending on what the shape looks like, how complicated the function approximation needs to be. But even this, like, another point, which we'll talk about more next time, is that in order to solve this problem, you don't need a perfectly accurate value function. Like previously, the way we solve these is we got an accurate value function, and then we use that to improve the policy in an iterative process. But
When you say value function, mean kind of like a Markov model of what's going on?
no, the value function is like this, like from chapter 9, what we just went over. It's the state values. It's the estimated value at every state.
Oh, okay, gotcha.
Or state action pair. The Markov, I mean, the problem itself, in this case, like for the random walk, is simulated with a Markov model where it's, stochastic. This case, the model is deterministic. I mean, there's other techniques earlier in the book that we went over in a previous time where you actually do instead of just taking gradients or whatever we did here, you actually take the data you've collected and you use it to build a model, like a model of the environment, and then you use that model to solve the problem. That's a whole different set of techniques that, we didn't go over this time. I mean, even these memory-based methods I talked about, these methods also don't, have a parameterized model, but these could also be used for the control problem. But again, like these kernel methods rely on building this memory, and the way the memory is built here relies upon completing episodes. And for this problem, it might not work because it might take too long, to build a memory because we may not even be able to finish the episode. I was looking at, it might be possible to use the memory-based method with bootstrapping, but that gets a lot messier because then when you build the memory values would actually depend on the previous values already in the memory and the kernel function. And I think that's not really the intended purpose of this memory technique. So I think this works better when you complete episodes. But yeah, I'd say having intuition about how elaborate like the neural network or the feature vectors have to be to solve the problem is not really intuitively obvious. And the best way to figure it out is just to do some tests, and hopefully you have a good sense of how to do good exploratory tests. Yeah, I'll also mention the next time there is some sort of other thing I did to test this problem, which doesn't really fit. It's more akin to what you're talking about of sort of building an approximate model of the true problem and using that approximate model to see what the solution looks like. So that's another, but I'll go over that next time.
Including like hidden states too and stuff like that.
Well, in this case, there's no need for, I mean, the state is just the position and velocity of the car. The the whole reason we're doing approximation is these are continuous values. So we can't like have a separate estimate for every state because there's an infinite number of them. But in this case, like the parameters, the feature vectors, whatever approximation technique we're using is we're sort of, compressing the information about the visited states. But yeah, you can apply a lot of the techniques in this approximation section of the book also apply to hidden or partially observable Markov processes where there is state information that isn't available to us. Like here, we're saying like we have access to this state information to solve the problem. But it turns out like if you add another state variable, like maybe there's like friction or something, which is part of the state, but you don't have access to it, that ends up being equivalent to just needing to approximate the states because we have to sort of compress all the information about the hidden state because we can't observe it directly. So we need to sort of have an approximate value of what that hidden state or what the impact of the hidden state is, depending on what state we're in. But yeah, doing all the reinforcement learning with partially observable or hidden states is very similar. A lot of what you have to worry about it and the techniques end up being very similar to having, fully observable states, but where we're forced to approximate the values somehow. Right. Another way to think about it is like whatever our approximation is, even though like we have the exact state we're in, we have to sort of map it on to previous states where we're sort of we are grouping states together in some way, whether it's state aggregation, which is very simple, or some very complicated way of aggregating the states. But that aggregation process sort of hides, the exact state information because we have to compress it somehow. Like in the memory technique, we compress it by, computing this kernel function for the states we've seen so far. But, with the parameter techniques, it's stored in the parameter weights, whatever they are.